Welcome back, student. In the previous lecture video, we already discussed that the strengthening mechanism and what is strengthening mechanism and what are the strengthening mechanism that a material can be strengthened by different types of mechanisms. So, as you know, that strengthening mechanism basically are there are four ways that you can that you can make the material strengthen. So, first was that we already discussed that solid-solid strengthening mechanism, in which we can say that this strengthening mechanism gives the material very strengthened by means of interstitials as well as substitutional solid solutions mechanisms. Okay, and another one was that the strain hardening due to the straining of the material means that first was in the tensile tested on an undeformed sample, then we are again retested after under deformed sample. What we get that particular experiment, that the result was that the yield strength is very much high compared to the undeformed sample. So as this you can weigh in this way, actually you can strengthen the material by means of solid strengthening mechanism as well as strain hardening. Okay, and another other two was that first of all this grain size hardening or grain refinement, and the last was that precipitation hardening. Now we will discuss on grain size hardening or grain refinement. It will also sometimes also called grain refinement. Okay. Now grain size hardening. The name suggests that we can make the material strengthen by introduce by or type produce uh, less number of or less size of grain to produce. Okay, to produce less number of grain means if you produce more number of grain size, more number of grain, then you can produce the coarse grain. Okay. Now, grain size hardening or grain refinement. First of all, we have to know that what is single crystal and what is polycrystalline. Okay, as it is single crystalline material and polycrystalline material. Now you know that the crystal structure and single crystalline material or single crystal means that the single crystal basically is in number of one, because there are only one crystal of theirs, then it's called single crystal. If in polycrystalline material, if the crystalline material is more than one, means crystal structure is more than one, that is called basically polycrystalline material. So this is the basic difference of single crystal and polycrystalline material. But in case of single crystal, what you see that all the unit cell, as you know, the single crystal, in a single crystal, the crystal structure in number is one. So obviously unit cell that are oriented, it's basically in the same way. But in case of polycrystalline, the unit cell are basically changed from region to region. As the region is changed from one region to another region, so obviously unit cell are changed. As you see this diagram, suppose this is your single crystal, in which you can see that there are some slip plane. These are the slip plane that these are the edge dislocations. You know that the edge dislocation or dislocation basically is basically one type of crystal defect. You can say the dislocation may be edge dislocation as well as screw dislocations. Now, if it is edge dislocation, then obviously it can be positive edge dislocation, it can be negative edge dislocation, depending on the size or depending on the extra half plane. If it is higher, if it is in the upward direction, there is an extra half plane, then it's called positive, and if it is negative, okay. So now here it is a positive edge dislocations which is moved through the slip plane. So these are sliding movement through these directions. Okay, so these are for single crystal. So as it is, the unit cell are oriented in the same way. So there is no barrier or there is no resistance to move the actually dislocations. Okay, so when you see in the polycrystalline material, what you see here that so there are number of polycrystalline, number of unit cell are there. There are various number of unit cell are there, which has basically changed from region to region. So suppose this is a crystalline structure, this is a crystalline structure, is the number of crystalline structure is more than one. Now in this particular crystal structure, there are one oriented unit cell, another in grain, another in crystalline structure, there are orientation is different. So if the orientation of unit cell are different, so obviously they will differ some boundary. At that particular boundary is called basically grain boundary. So grain boundary are also one type of surface defect, you know that. So grain boundary is very important for any type of material to produce. Okay, because this grain boundary can produce the material strengthening. How? Now question will be coming in your mind that how? Okay, now let's look into this picture, that is coarse grain, and this is picture suggests that this is a fine grain structure. As you know, the name suggests actually coarse grain. So the grain structure is very large. So this is the grain structure. So this is the one grain. This is the two number group, number three grain, number four grain. So what you see that in this diagram, that the grain structure or grain size is large. Okay. Now, if you see your fine grain structure in a particular material in a microscope, so what you see here that the grain structure are compact. Okay, grain are basically oriented in a compacting manner, and the size is small. Okay, this is the size is small very compared to this. So what you see here, so basically there's a in case of coarse grain or in fine grain, what you see here that the grain boundary, one grain orientation means unit cell orientation, the orientation of grain actually unit cell. That's these are the different that differ basically oriented by some grain boundary. Now number of grain boundaries is here. So these are the grain boundary. Okay, these are the grain boundary. So these are the grain boundary for what? For coarse grain. Now if you see the in case of fine grain, what you see here, if the grain number of size of grain is very small, so obviously the grain boundary, so these are the grain boundary 1 2 3 4 5 6 7 8 9 10. So there are there are a lot number of high number of actually grain boundary are there. So because if the grain boundaries increases in a particular structure of the material, as you know, the deformation. So deformation, because the any type of material for deformations, main cause is the dislocations. You know that because dislocation is the main cause for the deformation. Okay, now the dislocation may be edge dislocation, screw dislocations. Okay, now if the dislocation movement is resisted by some incident, by some phenomenon, some interactions, so they'll produce some resistance, they'll produce some resist of in a particular area. So here the grain boundary things here. Okay, things in this case. So as the more grain boundary in case of fine grain, so obviously if the grain boundary is more, so obviously more obstruction to dislocation. If there are more obstruction to dislocation, so obviously they produce more strength. Okay, so they produce more strength. So in this way you can produce more strength of in the material. So if you increase the means number of grain, that means if you decrease the number of size of the grain, that means the fine grain if you produce within the material, then you can produce the strength, then you can produce the high strength within the material. So in this way, by means of grain refinement, you can achieve the strength very high compared to the coarse grain structure. Okay, so these are coarse means grain size hardening or grain refinement. Now these are the very important point. So this main important point is that dislocation, more obstruction to dislocation. Why? Because there are more grain boundary. So in which case there are more grain boundary? In case of fine grains, because there are there are a lot of number of actually grains are there. So because if the grain size number is very less, that means actually the if the grain size is very less, that means the number of grain is very high, and obviously in number is very high, and obviously if the grain size, if the compact grain structure are there, so they'll produce high strength. So obviously, so fine grain can produce more strength compared to the coarse grain. Now regarding grain size hardening or grain refinement, one important equation of there's a Hall-Fetch equations. In these Hall-Fetch equations, so what you see here that the Hall-Fetch equation suggests that sigma y is equal to sigma infinity plus k divided by under root of d. So sigma y, as you name the suggest, sigma y means yield strength. Okay, yield strength, and sigma infinity yield strength at infinity, and plus k. K is basically constant. So sigma infinity and k both are actually constant term, and d is the grain. Okay, so sigma y, again I tell you that sigma y is the yield strength, sigma infinity and k both are actually constant term which is related with the grain structure, and d is your diameter of the grain. Now you know that if any type of material if you want to say that the material is very strength is very high or deformation is very high, so that indicates basically yield strength very high, right? So if the material yield strength very high, that indicates the material strength is also very much high. Okay, and they differ, basically they are relate from this relations with the, so in these relations what you see here, sigma infinitive and k both are actually constant term. So the main variable is that d and sigma y. Sigma y basically relations is that sigma y relations with that under 1 by under root of d, that means is inversely proportional with under root of d. So if the diameter of the grain is decreased, if the diameter of the grain is decreased, sigma will be increased, right? If d is increased, that means sigma y is decreased, means yield strength is decreased. What does it suggest? It suggests that if the diameter of the grain means diameter of the grain small, that means the grain is fine grain. Now in this case, yield strength is very much high because there are more obstacles for to dislocations, because there are more number of grain boundaries, and this will suggest and this will help you to understand the grain size hardening or grain refinement phenomena. And now if you increase the diameter of the grain, means if you increase the diameter of the grain means the grain structure basically coarse grain in structure. Now if the coarse grain structure are there, and if the the sigma infinitive and k both are constant are there, so obviously if the d is increased, sigma y will be decreased, means yield strength is decreased. Why? Because there is less number of grain boundaries, because in this case of, as you know, there is a particular structure of the material. In case of force grain structure, the grain boundary is less. If the grain boundary is less, that means less obstacles to dislocations, that means less strength, that means less yield strength. So that is the physical significance of Hall-Fetch equations. If you draw the Hall-Fetch equation on a particular graph plot, that is sigma y versus to 1 by root over d. So in this plot, what you see here, that if d is 0, d, it may be 0 because d is very small. It can be reached up to 0. When it is reached, it's 0, that sigma will be sigma infinitive. So these values, okay. And if you draw this diagram corresponding 1 by d, if you can plot this way. So you can plot, so this is the diagram, and this slope, the slope of the diagram actually plot, that indicates here k, okay. So this is the Hall-Fetch equations. Okay, in the next we did in the next the strengthening mechanism is that precipitation hardening. Okay. Now precipitation hardening. Okay. As you know that already we discussed that three types of strengthening mechanism, that solid-solution strengthening mechanism, grain refinement, as well as strain hardening. And the last one that you can make the material strengthen, that is basically precipitation hardening. Okay. Now, precipitation hardening also sometimes also called edge hardening. Okay. It is also sometimes also called edge hardening. Both are actually same. Precipitation hardening, sometimes also called edge hardening. Now, where it is used basically to strengthen the materials like non-ferrous type of material like aluminum, magnesium alloy, aluminum alloy, and also some ferrous type of alloy you can use to increase the strength of the materials. Okay, it is basically used to process the alloy, and there are some non-ferrous metals also are there. You can use this strengthening mechanism for particular that type of materials to increase the strength of the material. Okay. Now, why it is said as precipitation hardening, also edge hardening? Because as the name suggests, edge. Okay, so obviously the precipitation hardening, edge hardening, solid solution strengthening, grain refinement, all this because of the increase the strength of the materials. So this edge hardening also because it's one name of precipitation hardening, and why it is called as edge hardening, because of the strength is developed. Because the strength developed with time. As much as you can give time for the material, the material can absorb some, produce some strength. So what is the mechanism for that is very interesting. Now what is the mechanism? That, as you know, that precipitation means precipitate means there are another single second phase are there within a particular material of a matrix phase matrix. When a particular phase matrix of the material, Another second phase are introduced. So this second phase actually, which is basically small in size, they produce the insignificant increase the strength, enhance the strength. So that's why it is called precipitation hardening, because there are some small teeny particles. That small teeny particles increase the strength of the materials. Okay, that particular small teeny particle which is basically dispersed throughout the materials, throughout the parent phase of the matrix. That's why it is called precipitation matrix, precipitated particles, and the hardening process, that's why called precipitation hardening. Now let's take a look into this. The strength and the hardness of some metal alloys may be enhanced by the formation of extremely small uniform dispersed particle. That actually small dispersed particle is basically called precipitates. Okay, means small precipitate. But what is the mechanism for to produce this type of small teeny particle, which is basically called precipitate? The mechanism is that you know that the deformation is two types. We already discussed on that. Deformation is two types: plastic deformation and elastic deformations. Now during the plastic deformations, actually these precipitate particles are actually in action. Okay, so basically these precipitate particles, when they are produced, precipitate particles, but how do you produce precipitate particle? We can go through this, but as we produce the precipitate particles on a particular present means parent phase of the materials, so there are some zone of precipitate that act as an obstacle to dislocation motion. So again, as you know, like grain boundary, in case of grain refinement, instead of the grain boundary are there, so because they are resist, they are actually act as an obstacle. Here, that precipitate particles act as same, because these precipitate particles are act as a obstacle for the dislocation motions. When they are resist the dislocation motion, or when they are actually obstructed by the precipitate particles, so obviously they are increase the stress, because they increase the material, they increase the stress. That stress must be increased to push the dislocations. Okay, if there are no precipitate particles, so easily dislocation means edge dislocations can move or gliding through the slip plane easily. If there are some precipitate particle are there, if the edge dislocation move if they move throughout the slip plane, so obviously they introduce some extra stress to push the dislocation. So there are some extra strain will be involved in the particular manner. So alloys becomes what? Harder and strength. So in this way, actually, you can increase the strength of the materials. So as like, because the main thing is that you have to increase the materials to obstruct to reduce the dislocation movement. So that's all. Okay. So what is the main process to produce actually for precipitation hardening? Because precipitation hardening actually is a one type of, you can say, the quenching and precipitation is a one type of heat treatment process. What is the step which is basically introduced in the precipitation hardening? You can show that the first step is that is solution heat treatment. Okay, solution heat treatment means obviously you know that what is heat treatment, what is the necessary and what are the objective of heat treatment. Now here is solution heat treatment. So one term is added here into heat treatment, that is solution heat treatment. That indicates actually solute atoms are dissolved to form a single phase solution. So that's all for solution heat treatment, and they are generally solution heat treatment is basically done around 1200 degrees centigrade, or depending on the types of material, if it is ferrous type of material or for steel, or medium carbon steel, actually the solution heat treatment temperature is around 1100 to 1200 degrees centigrade. So because of to dissolve to form a single phase solutions. So if you look into this diagram or temperature time plot for the heat treatment process, you can see that this is a starting point. If you heat the material on a particular temperature, suppose this is a solution heat treatment temperature is P0, that in this temperature what happens, that all the solute atoms that are dissolved to form a single phase solution. So in this region or in this temperature region, there are solution heat treatment process occur. This solution heat treatment process occurs to dissolve all the solute atoms within the solvent, because of to form the single phase solution. So in these temperatures, there are one single phase solution are there. Now quickly you have to quench, quickly, just in a few seconds, a fraction of second, you have to quench, because to prevent the diffusion and to form the second phase particle, or you can say this to form the supersaturated solid solution. The quenching process takes place because you have to form the supersaturated solid solution, because to prevent the diffusion and form the small particle, that small particles actually your precipitate, and that precipitate actually act as an obstacle for the dislocations moment. So that's why the name is precipitation hardening. Okay, now this is not enough. Now here is a quenching process is here. So quenching process is done by either water, or that some type of salt water, or you can add as a ice. Okay, depending on the quenching medium, depending on you can get your cooling rate. So there are some supersaturated solid solution you can get in a particular this zone. Now there are one step that name is aging. So that's aging step, that's what is called age hardening. Aging is something where the stain actually develop with time. So that's why it's called aging. Okay. Now heated supersaturated solution to you have to heat it to a intermediate temperature region. So this is the intermediate region of this if you heat, so the T1, this is T0, T1 plus T0 by 2, that will be T2 here. Okay, you have to heat up to intermediate temperature. Okay, to intermediate temperature, and there are some precipitation, they will form a particularly precipitation heat treatment occurs here. Okay, in this zone actually precipitate particle will form here. Okay, again you have to cool on a particular in normal way, normal temperature, normal air. Okay, so in this way actually precipitate particles are formed out in a particular suitable heat treatment process, and that particular suitable heat treatment process from the precipitate particle you can introduce the actually parent phase of the material. So if you add some precipitate particle in the parent phase of the matrix or parent phase of the material, so obviously they will they will act as an obstacle for the dislocation moment, as well as they introduce or they increase or they enhance the strength. So in this way you can increase the strength of the material. So we discuss all four types of strengthening mechanism: solid strengthening mechanism, drain definement, stain hardening, as well as precipitation hardening. Okay, thank you very much for listening and watching me, and goodbye.